Today we are looking at the Reynolds number, a fundamental concept in bioprocess engineering. By definition, Reynolds number is a dimensionless variable that is used to characterize fluid motion as either laminar or turbulent. Conceptually, it represents a ratio of two opposing forces. Therefore, we can define Reynolds number as inertial forces divided by viscous forces. The inertial forces drive the fluid forward and it promotes the mixing, whereas the viscous forces they resist the flow and keep the fluid organized. This is the basic concept of the Reynolds number. Now let us look into, and this is the flow of water in the pipes. This is the input, this is the output. Engineering textbooks introduced RE using flow through a circular pipe. This is given by the equation RE is equal to D. Here are the key variables where D is the pipe diameter, this is the diameter of the pipe, that is D, and U is the linear velocity, is the linear velocity of the fluid, that is U. Rho and mu, they are density and viscosity. Density and viscosity of the fluid. This formula works well for transport, but in biotechnology we have a different problem. So that is flow in bioreactors. Flow in the bioreactors. In a biopharmaceutical industry, we are primarily concerned with mixing in a stir tank bioreactor. So in a stir tank bioreactor is nothing but there is a bioreactor and there is the stir inside this. Since the fluid is being driven by the impeller and not by a pump, we must have to change this equation to REI is equal to NI DI square rho divided by mu. Here we got to note the critical difference. Instead of the linear velocity, in the above case, we have used U. U was the linear velocity, but here we are using N, which represents the stirrer speed, because here we have a stirrer, and so we are going to replace U with N, which is the stirrer speed. Usually it is in revolutions per second. So instead of the pipe diameter, we use di, the impeller diameter. Here we have used d, which is the diameter of the pipe, but here we are going to use the diameter of this impeller, which is represented as di. Also note that the diameter is squared, okay, in this equation. This means that the geometry of your impeller has a much strong impact on the flow regime than the speed does. So the value of RE tells us the flow regime. So the value of Re tells us the flow region. If the Re, that is the Reynolds number, is low, if the Reynolds number is low, the viscous forces are going to dominate. Viscous forces dominate, and the flow will be laminar. Laminar means the flow is smooth. It is a laminar flow, which is a very smooth flow. But if the Reynolds number is high, then there will be, it is not a smooth flow, then there will be inertial forces. Inertial forces are going to dominate. When the inertial forces dominate, then the flow becomes chaotic. So it's not a linear, it will be a very turbulent and a very chaotic fluid flow. In a reactor, we typically aim for turbulence to ensure oxygen transfer, but we calculate Re to ensure that shear stress remains safe for the cells. If you have any questions about calculating this for your specific process, drop them in the comments. I hope this is clear. Thank you so much.